When scientists discovered the internal structure of the atom, namely the nucleus, they had a problem on their hands. They had a conundrum. The issue is you have all these protons and neutrons crammed into this small area, the nucleus, of course. And why should they be there at all? With regards to the protons, they should be repelling each other, and so as a consequence shouldn't be in the nucleus. And the neutrons, what's keeping them there? They're neutral. So they have no electrostatic interactions. Why are all these particles crammed together in the nucleus? And pretty quickly you reach basically the only possible explanation, which is that there must be a force strong enough to overcome the electrostatic repulsion of the protons, and this force must also include the neutrons. And indeed, there is such a force, and we refer to it as the strong force because it is strong enough to overcome the electrostatic repulsion. It only exists over very short distances, and it only acts on protons and neutrons. In other words, it only acts on nucleons, the particles that are found in the nucleus. It doesn't affect any other particles, just protons and neutrons. And it's strong enough to overcome the electrostatic repulsion and keep the nucleus together. Now, there's a few things about the strong force, just about the nucleus in general, that we need to understand. You start with, of course, a single proton, hydrogen. Okay? With a single proton, you don't need a strong force. There's nothing to repel. There you go. That's your atom. That's your nucleus. Everything's fine. But when you get to helium, the most stable isotope of helium is helium-4. It has 2 protons and 2 neutrons. Okay, why the 2 neutrons? Because you've got to have something to help keep the nucleus together. The electrostatic repulsion of the 2 protons is pretty strong, and the strong force isn't strong enough to always win. So the neutrons are there to provide more strong force, to provide a stable configuration and keep the nucleus together. You need to realize there's always a tug of war between the strong force and the electrostatic repulsion. And, for a good number of atoms, a good number of nuclei, the strong force wins. But there are isotopes, and remember, an isotope, it has the same number of protons, but different number of nucleons. So isotopes have different numbers of nucleons from each other, but the same number of protons. So some isotopes are stable because they have the right configuration, and others aren't. They're going to decay radioactively, we say, because at some point the strong force isn't strong enough. The configuration is just right, that the electrostatic repulsion is too much, and consequently the atom is going to some extent break apart. There's going to be some decay. I'm simplifying the overall interaction there, and exactly how radioactive decay works, but that's the general gist of it. Now, as I was saying, there's some things to realize about the nucleus and the strong force. We just talked about, as you move forward, when you get to helium, you need those neutrons there, and so on and so forth, actually, as you continue up. You need, generally speaking, the same number of neutrons as protons, or at least that's what you find up until about, I forget where it is. Is it calcium? I think around calcium, you start getting more neutrons than protons in the nucleus because the electrostatic repulsion is just so great. I mean, here with calcium, you've got 20 protons crammed in there. Then you get to scandium. You're talking about 21 protons. That's a lot of repulsion. And, this just keeps going, and you have to cram more and more neutrons in there to keep it stable. And eventually you get to lead. Lead is the last element that has a stable configuration, that has a stable isotope. After lead, everything is radioactive. Now, bismuth, it should be noted, bismuth is essentially stable. Its half-life is more than the age of the universe. So bismuth, it was only discovered to be radioactive in, I think, 2003. So it has an incredibly long half-life. So yes, technically it's radioactive, but for practical purposes, it isn't. But everything, like I said, everything over here is radioactive. So that's 83 and above. And why is it radioactive? Because the electrostatic repulsion is just so great. It's so great, it doesn't matter how many neutrons you shove in there, there just isn't a stable configuration. The repulsion is eventually going to win out. And this puts a limit, essentially, on how big atoms can be. Now, we keep making bigger and bigger elements. This periodic table doesn't go up to the biggest ones, but we keep making bigger and bigger elements in colliders and whatnot, wherever they're making these things. But when they make them, they only exist for fractions of a second, very small fractions of a second. And that's just because the electrostatic repulsion is so big. Again, that repulsion puts a limit to the size of a nucleus. And, in that sense, it kind of helps to explain the periodic table. Just part of it, of course, not all of it. But that's the idea. These are the things I want to talk about. Strong force, it is very important. It does matter with regards to the size of nuclei, why there is the largest, why the neutrons have to be there. And it explains even why there is a nucleus. Without the strong force, we would only have the hydrogen atom.